Great. Welcome, everyone. Thank you for joining us for today's webinar. My name is Alejandro, and I'm going to be today your host. Today, we're presenting an X-ray view of astrophysical black holes by Javier Garcia. So, hold on. I have an issue with... okay, I was getting a feedback. Sorry. Okay, so let me talk a little bit about Javier. Javier is a research assistant professor of physics at Caltech and a humble fellow since 2017 that he took to Remeis Observatory in Germany. He obtained his PhD from the Catholic University of America in Washington, D.C. in 2010. Then he did a couple of postdocs in Maryland, CFA, Harvard, Smithsonian, and Caltech. But before that, he got his bachelor from La Universidad de Zulia in Venezuela and a master's in physics from the Venezuelan Institute of Scientific Research. Javier simulates the interaction of gas and radiation in the very hot vicinity of black holes and works in the New Star team at Caltech. In collaboration with many other scientists, he has developed a state-of-art model for the X-ray radiation around black holes that is widely used in the community. So remember that you can ask questions over email through our YouTube channel or Twitter, and the questions will be read at the end of Javier's talk. Now, without further ado, we will turn it to Javier. So please share your screen.
Thank you, Alejandro. Hi, everyone. It's a real pleasure to have the opportunity to talk to you. I may have been a little bit bad on following on the talks on live, but I've watched many of them on YouTube. So I think it's a great idea. It's a great initiative, and I'm certainly very happy to be part of this. So I'll talk about something that is central to my research. As Alejandro already mentioned, I work with, I try to model the interaction of radiation and matter in the vicinity of black holes, and we use this to learn physics about the systems. I think until very recently, this was the only way to really access this sort of these quantities, and I say until now because now you all have seen the really nice picture, the first direct image of a black hole by the Event Horizon Telescope collaboration, and also we getting a lot of new discoveries with LIGO by detecting gravitational wave signals from merging of two black holes. But this is just literally happened now. For the past, I'll say 40 or 50 years, maybe a little bit more, really the best and almost only way to detect black holes and learn about them was through the very energetic electromagnetic emissions in their vicinity. So this is mostly happens in X-rays. You also see gamma rays and radio and sometimes optical, but X-rays have a very particular usefulness for understanding black holes. So that's what I mostly do. So the outline of my talk is going to be very, very short history of black holes and X-ray astronomy. They go kind of hand in hand together. And how do we model the emission and reflection of the radiation with and without GR? I'll talk about my current research on black hole binaries. These are systems where you have a black hole and a stellar companion, and how we use the models, and together, of course, with observations to derive quantities about black holes, such as their angular momentum or spin. And we learn a lot about the disk and this other region called the corona, which is where most of the X-rays we think are emitted. And also something that is happening much, we really now start learning more about the microphysics of the material of the accreting outflow. So I'll say some new things about that. So to high, and typically we're talking about 0.1 to 2, or a bit more kV. Are never very well defined. We're talking about kilo electron. be between 0.1 to about 100 angstroms. If you use Wien's law, then you're talking about temperatures of between 1 million to 100 billion degrees. So we're definitely we associate X-rays with very high temperature environments. They can be produced by non-thermal particle acceleration, for example, in strong magnetic fields, and they either produce or induce atomic transitions that involve the innermost shells in the atom. So whenever you talk about X-rays, if you think about atoms or atomic transitions, you're thinking about transitions that involve the deepest levels in the atom. So X-rays were discovered. It's one of the funny stories of physics. They were discovered almost by casualty by this German researcher Wilhelm Röntgen, and he was doing experiments with cathodes, and essentially almost by coincidence he realized that there was some emission that was energetic not to pass through thick materials, and then he started figuring out there were some mysterious rays coming out from his experiment. He called it X because he didn't know how to call it, and he figured out this had to do with some very energetic particles. And there you see his picture, and also the first radiography of the hand of his wife right there. So he was brave enough to experiment with his wife. So there you go. That's the first medical X-ray in history. So at the same time, I'll say, not at the same time, sorry. Well, roughly at the same time, I'll talk in a minute about general relativity and Einstein's theory of general relativity. So that was happening pretty much at the same time, but it took quite many years for X-rays to make it to astronomy as a band that people will study. And this also happened in a kind of a funny way. There were people like Ricardo Giacconi here who thought X-rays were interesting to study in astronomical sources. We were talking about back in the 50s or 60s, where there's about it, and all that people knew was that the sun X-rays in the sky. So they were trying to study the sun and observe X-rays. The problem is the atmosphere, the Earth atmosphere is opaque to most X-rays, so you need to kind of go above it. So they have to convince agencies to build either balloons or sounding rockets to go above. So that was one of first Giacconi's ideas, and the way they sold it to the U.S. government is to say, well, we can put essentially like a Geiger counter and it's a super, and look and spy on the Russians and see bomb testing or something, atomic bombs, X-rays coming from those, whether they're doing or not, of getting funding. But they were, of course, looking down, but also up. So when they were expecting, they were sun to be brighter, they found it was much brighter towards the so they call this source Scorpio X1. Obviously, once again, X know what it is when detected, and it's the first X-ray source other than the sun discovered. Only gave birth to X-ray by doing this kind of measure, and we now know this is an actual where there is a compact object, not a black hole, but it's a neutron star. But they have very, so X-rays definitely open a whole new window to see kind of physical process system. This is, for example, supernova PIA. You see it in the optical, and you see this shell expanded after explosion in the visible. But then if you look at it in X-rays, it's quite different, as you can see. The different colors here represent different temperatures emitted by different ions. So you see green, yellow, red, and blue. There, you have different material moving at different velocities at different temperatures. So it is quite a contrast what you can learn by looking or flipping, like I'm doing right now, between optical and X-rays. And if you pay attention in the middle, there is this little point, which is it's not a bad pixel. It's actually a very strong X-ray emitter, and we now know this is a neutron star. That is the remnant of the left after the supernova explosion. So again, at the beginning of last century, Albert Einstein came out with the general relativity theory, and that also opened up a whole, as you very well know, a whole other set of new ways to look at the universe. And we now understand that space and times are not absolute; they're interconnected. And the Einstein field equations were first solved by this other guy, Karl Schwarzschild, in also in 1915. Very soon, right after Einstein publishes his first paper on general relativity. And this is also a beautiful story that I always bring on my talks. I think it's quite remarkable that he was able to do this during the war. Literally during the war, he was just reading Einstein papers and working on this. He died shortly after this, but he provided the first exact solution to Einstein field equations for a non-rotating mass. So this is what we now refer to as a Schwarzschild black hole, which will be the solution of a black hole that is non-rotating. And you might have heard of things like the Schwarzschild radius that sets what will the event horizon of this kind of black hole will be 2 times G over cm squared. So after all this development, after Giacconi discovery, then many other observatories were launched, either by rockets, as I'm saying, sounding rockets that are suborbital flights, or balloons that can go high above the atmosphere, such as you can actually detect X-rays. And these are just a couple of examples of the early observations. Just a few points, as you can see in the spectral energy distribution. If you're measuring different energies, you try to come up with something that looks like a spectrum. So the initial ones were obviously very limited, but by the 1980s, there was already enough sensitivity in the detectors to observe X-ray sources that were identified spatially with galaxies that were very people understood immediately that this emission, the X-ray emission, were coming from these galaxies, most likely from the nucleus of the galaxies. So that's what we refer to an active galactic nuclei, or AGN. And by looking at many of them, we see people saw that their spectrum looks in general like a power law continuum with a photon index around about 1.7, or nowadays it's more about 2 is the standard distribution of energy. But when a lots of them were observed and put together, they come up with enough signal to detect that it was not just a pure power law. There were some residuals, as you see in the plot down there on the left. And that little peak there is placed at an energy that corresponds with emission. Inner shell iron emission is also referred as iron K emission. K is because in the atomic model, the K shell is the innermost one. So it became clear later in the 90s with better CCD detectors that there were enough atomic features in the spectra, and when similar spectra were taken from other AGN, they were able to identify much better the iron K emission. There also something happened, and is that they realized that the emission is not symmetric. It's actually quite asymmetric and skew, as you can see on the also on the left bottom panel for a famous AGN galaxy MCG -63015. And people were quickly realized that this could only be explained if you include relativistic effects. They figured out, well, this is coming from the center of galaxies, and we believe there might be a supermassive black hole in the center. Then if this emission is produced close enough to the black hole, then there might be effects that change the way the line looks like. So in fact, when you think about accretion into a black hole, the first thing that comes to mind is an accretion disk, and this is because of conservation of angular momentum. All the accreted material will tend to form a flat structure, circling around, spiraling around. So it forms a relatively thin structure or disk, but it doesn't go all the way to the horizon. There is a point, there is an actual sharp edge to the disk where there cannot be more circular orbits. So it's called the innermost stable circular orbit radius, or ISCO. For any particle beyond this point or closer to the black hole from this point, it will essentially plunge directly. So it will not spiral anymore. It can't sustain any kind of orbit. It will just go directly. So as a proper structure, as a disk, that's where it will stop. And going back to the idea of the relativistic iron line, so this shows a little bit more what I was mentioning about the relativistic effects, and what happens to a single line, a single photon, or not necessarily a single photon, but a line and a single energy that is produced at a particular orbit in a rotating disk. So Newtonian physics will tell you that you should see a double horn structure, because you're going to see part of the disk that is receding from you and part of the disk that is approaching towards you. So one part is blue shifted, the other one is red shifted, and then you have the double horn. But because of a special relativity, the part that is blue shifted is going to be boosted. It's going to be boosted in intensity towards you, while the part that is red shifted is deboosted. So that's what you see in the second panel, the asymmetric double horn. So one is going to be more intense than the other. And then general relativity will add the additional effect of the gravitational redshift. So the entire structure gets redshifted by gravitational effects. So this is on top of the standard Doppler redshift, right? So when you combine all this, you get this line profile that actually seems to fit well what it was observed back in the 90s. And you see there is in the right panel, I show the difference in a line feature for a Schwarzschild black hole and for a Kerr black hole. And the difference, as I mentioned, Schwarzschild is the black hole that has zero rotation, while the Kerr comes from the Kerr-Newman solution. That's the case of a rotating mass. So for a maximum rotation, you see that the shape of the line is actually different. And this is because this has to do with the location of that inner radius of the accretion disk, or the ISCO. That location, the place where the accretion disk edge ends, is dependent on how fast it's rotating, because frame dragging effects and other things, it will move around. So in the middle, I show the non-rotating black hole. It's the innermost radius is set a certain distance. Then if you have maximum rotation, like in the bottom panel, it moves closer, a lot closer, almost touching the event horizon. And the other extreme case will be maximum retrograde rotation. That will be, the disk and the black hole spinning in opposite directions. And in that case, it actually moves farther away. And because you're changing the location of the accretion disk, you also change the location of where the spectral features are being produced. Of course, how close to the black hole are they being produced, and therefore the gravitational distortion they suffer is going to be different. So in this way, you have some sort of a direct connection to the spin of the black hole, and this has been known for quite some time. You have a monotonic relationship between the spin and the position of the ISCO radius. We typically we typically measure this with a dimensionless spin parameter that I'm showing here, Cj over Gm square, where J is the actual angular momentum of the black hole. And you see here two cases for zero spin. It will be A star 0. This spin parameter 0 is obviously non-rotation, and for a 10 solar mass black hole, the radius of the ISCO will be about 90 kilometers, as opposed to the maximum rotation, where you have a radius of 15 kilometers. So this is the kind of small spatial differences that we're trying to measure here. With modern observatories, things have gone, of course, a lot better. I have worked a lot with a satellite called RXTE, the Ross X-ray timing explorer. It was already decommissioned in 2012, and it had a resolution of about 1 kV at 6 kV. And I showed an example there from a paper a few years ago, and I'll talk more about that particular case. These two cases are the same object. It's a black hole binary in our galaxy GX339-4. The one on the right is data taken by two newer instruments, NuSTAR and SWIFT. NuSTAR is the color one. So you see on the top the actual spectrum, the detected counts in X-rays in a much broader band, and the level of background noise that you have, or background counts from the sky or from the instrument for anything else. And you see how much better the resolution has gotten. It's 0.4 kV at 6 kV, so it has improved a lot. In the future, we expect things dramatically better. So this is what is being currently worked on for future X-ray observatories. This is a European mission called Athena that will have 5 EVs. So we're talking about 1 kV at 6 kV, where we're talking about just a few electron volts at the same energy. It will be remarkable what we can see, and then definitely get a lot more detail of what's going on in this system. So there's a clear need already, and it will be even more in the future, for models that work on that are capable to reproducing these sort of observations. And this is really important, because the physics that we're talking about, this physics of accretion, emission of X-rays, and all this is applicable for in a wide range of masses. It's observing neutron stars that are in binary systems. It's definitely observing stellar mass black holes that are also in binary systems, and it's also observed in supermassive black holes in AGN, which also have they don't have a companion, but they have a whole galaxy to supply gas, and they also form accretion disks. And the phenomenology is pretty much similar. The scales, the time scales are different. The mass scales are certainly different, but the rest, anything that is mass invariant will kind of apply equally. So what I've dedicated a lot of my effort is in precisely modeling what the X-rays look like near the subjects, and in particular the component that is reflected from the accretion disk. So I'm not going to go through the details now. Just if anybody obviously is interested in this, it can contact me, and I'll bore you to death with the details. But it suffices to know that it's a fairly complicated problem, because you need what you need is to solve the problem of rigidity transfer in an optically thick gas, put in a lot of lines. So that requires a lot of first a lot of knowledge on the atomic physics. So you need atomic quantities for all astrophysically relevant ions for as many lines as possible, but then that makes the calculations quite CPU intensive. So we've done this. This is just an example of one calculation where we solve for the ionization structure of a gas that is illuminated with X-rays. We see the changes in temperature, and then we see what the reflection spectra comes back. So in the right, I'm showing the spectrum in X-rays. If you illuminate a parcel of gas with a power law, like they continue observing in most of these sources, which is shown with the dashed black line there, then what you might get back, depending on the situation, is something like the blue line, which is a very rich spectrum with a forest of lines that are both emission and absorption lines, and there are features that have to do with electron scattering as well. So we need to essentially do this as best as we can before we can reproduce the observations. These are more examples of how things change with the parameters in the model. Most of the models are going to be parameterized with this ionization parameter that has to do with the flux that goes into illuminating the disk versus the density. And that essentially gives you a measure of how ionized the gas can be. And if you look at the numbers, and you don't need to understand the details of it, but obviously that psi number, that ionization parameter, the larger it is, the more ionized the gas will be. So you see the changes in the spectral features as you increase more and more the ionization. This can be done by increasing the flux or just decreasing the density. Once this is done, that it takes for essentially you have to cover a range of parameters and make a table of many synthetic spectra. It could take, you know, the order of a million CPU hours. Then you have to include the relativistic effects as a post-processing technique, and we do this by a ray tracing convolution. Essentially, you follow photons in a curved space-time, and you predict what the effect is going to be given, you know, their position in the disk and how the illumination of the disk was produced in the first place. So this is all combined in a single model that people can now use to model any given observation in X-rays. So the model parameters are many, but that's this good thing and a bad thing. It's a bad big thing because then you have too many degeneracies sometimes, but it's a good thing because essentially the model is sensitive to many important physical parameters. And then you see, once again, the spin of the black hole is one important parameter you can measure. The energy of the accretion disk might not be right at the ISCO, and you can also measure if it is highly truncated or not. The inclination of the disk is also very important, and then it will change the amount of relativistic blurring you have in the spectrum. There are many other parameters like you know, the iron abundance or things that have to do with the illumination of the disk. I'll talk a bit more in a minute. So this is the complete sort of cartoon picture that we have within what happens near a black hole. You have then an accretion disk, and then you have some a strong emission of this power law that I mentioned before. We don't clearly know what it is, but the most famous idea is that you have Compton scattering in some sort of corona, very hot plasma is Comptonizing photons that were emitted initially from the accretion disk. Thermal photons the gain energy in a hot electron gas of electrons, and they produce a power law like the blue spectrum that I show on the top. And then if this part of this radiation goes to the observer directly, and you see it essentially as a power law in energy. But if it illuminates some other part of it, illuminates the accretion disk, then you're gonna see the reflection features that I mentioned a second ago. If the reflection is far enough, so you see something like the green line, you see sharp emission features. Those are the two big ones that are actually from iron, the K shell. But if the emission is relatively close to the black hole, then you're gonna see the relativistic effects, and sometimes they can be so extreme that they completely blur out the spectrum, they smooth everything out, and essentially something like the green line or the green spectrum will become something like the red spectrum there. It looks almost featureless. There are features that are just very soft and smooth. So this is just to say also that the panel on the top is an actual fit to real data taken from this black hole binary system GX339-4. So this is at the bottom is a cartoon, the top is real science done. So you have a combination of all these different components. And as this is, I'm just repeating myself a little bit. This is just to show more clearly how a given model will change depending on how you change the parameters. So here I'm showing 4 important physical quantities. The spin, the more spin you have, the more blurring of the iron line you see. But it's not just the iron line, you see the entire spectrum changing to a certain degree. But then there are other quantities like the coronal high, and is it how high this primary source of X-rays is placed above the accretion disk will change things because it changes the way it gets illuminated. And that radiation is also affected by relativistic effects because you can have beaming of the photons that go towards the disk. So the closer you place this corona, the more beaming it acts like a magnifying glass. It just focuses all the radiation in a tiny region very close to the black hole. So you see when H is small, you see this extreme blurring of the spectrum. And of course, things that I mentioned, inclination, essentially moves the blue side of the line. You see it moving towards the right, the more inclined it is. And iron abundance, of course, will make the iron features more prominent, but it also increases the photoelectric absorption near the line. So it makes both, increases the emission, but it also somehow decreases the continuum around the line. So all these things are important, of course. And so far, using this technique, we have measured spins for several supermassive black holes in AGNs. This is in the figure in the bottom shows an actual distribution of spin versus mass compiled recently by Remeis and also by Sudaman in 2016. And the problem here is there is a lot of there are many big error bars, as you can see. So the actual determination of spins is not always very well, is not very accurate. And this is something we're currently working and trying to reduce those uncertainties and get a better distribution. So you essentially, we need a larger number of objects, but we also want, it doesn't really help too much to increase the sample if we don't have good constraints. However, this already shows something interesting, which is most of the spins, and actually the better measured ones, are closer towards the maximum value. So it means that most of the black holes we see, the supermassive black holes, are actually rotating close to their maximum value. And this is important because this distribution can actually help to constrain theoretical models for the formation and evolution of supermassive black holes, because different models that are based on different prescriptions, whether black holes grade by steady growth or whether they are by mergers, and if these mergers can be chaotic or can be hierarchical. So there are many different proposed channels for the formation and growth of supermassive black holes. These different scenarios will then predict different distributions for spins that you will measure today. So we can actually have a very good distribution measure. We can go back to the theoreticians and say, all these models are wrong or are rejected, at least by the observations. These are more likely to be the right ones. In the case of black hole binaries, and again, when I say black hole binaries, this means stellar mass black holes with a stellar companion, which are the systems that we can study with X-ray reflection. You see a list. Is maybe not very well, it's not very clear, the names, but it doesn't matter. What you see is a compilation of more or less where we are with measuring spins. So in this case, there is some sort of like a better picture. There is a wider distribution of spins, but also, I'll say, there are slightly better constraints. There are still some cases, especially towards the lowest spin, that are difficult to measure because typically those are the ones where you see a narrower line. So you need better data in order to have a better constraint of the spin parameter. But it's not all roses, it's not all great, because, for example, in the case of SIGX1, which is a very famous black hole system, when you look at the reporter values in the literature in the last 10 or so years, you see a dramatic change of both accuracy and the precision of the measurement. So I say that that's not a real trend. It's a real trend because it exists, but it's not a physical trend. It's not that the spin is changing. What is changing is the quality of the data and the quality of the model. Hopefully, we're getting smarter in understanding how to fit these observations and derive a proper quantity that actually makes sense. So we're now consistently getting to agree that the spin in the system is close to the maximum. There are other things very interesting that you can do with reflection spectroscopy, and you can look at evolution of things like the corona and the accretion disk, especially in black hole binaries, because given that there are smaller systems, the time scales are much shorter, so they evolve much faster in time. So for the corona, we always call it some sort of a mysterious thing, because it's something that has been proposed, but we don't understand much of what is its origin or even the geometry. You can play with different models that say, well, it could be a sphere, it could be just this spherical gas of hot electrons near or around the black hole. It could be a sandwich in the disk. It could be some sort of a slab, or it could be a point source sitting on the axis that will resemble something like the base of a jet or something like that. So depending on what you assume for the geometry of the corona, you're going to get different reflection features or slightly different behavior of the system. So we're trying to learn what is the connection between the corona and the disk and how the two of them evolve. One way to do this is obviously observe systems for a very long time. And what I'm showing here in this little movie is actual data from the satellite RXTE taking over, I'll say over a decade for this source GX339. And you see these tracks that they're doing in this plot is showing, in the y-axis shows the X-ray luminosity, while in the x-axis it shows the spectral slope, meaning the spectrum is changing quite a lot, but it also is this luminosity, because these sources typically go into what we call outbursts. So they flare up in X-rays for a relatively short amount of time. They evolve, lots of changes happen, and then they go in quiescence again. They kind of are all barely detectable or simply non-detectable in X-rays. So we're trying to understand and follow this evolution with the rich amount of data that we have in hand. This is to show what the hard and soft state looks like. Hard state because the spectrum looks hard, meaning it has most of these photons in high energies, while the soft state is, most of the signal that you see comes in soft photons, soft X-ray photons. This is because one is dominated by non-thermal emission, power law. The other one, the soft state, is dominated by thermal emission likely from the accretion disk. This is another example. This is SIGX1. Look, with almost every single X-ray instrument in both the hard state and the soft state, and you see this huge dramatic difference in the spectral distribution. You have to think about, in terms of energy, how much energy is put in photons. For example, in the hard state, you have most of the energy coming at 100 keV, while in the soft state, most of the energy is coming close to maybe a few keV. So this is a huge difference in terms of energetics. So there is something very, very big and dramatic changing in the system to behave in this way. And the time scales for changes between these states can be between weeks and months. So it's relatively short. It's quite impressive. So we follow in the hard state one of these sources, GX339, and we look at the spectrum. When you feed a continuum to all the spectra, what you see is something like this. You see very clear features of reflection, the iron K emission, what is called the iron K edge is an absorption feature, and also the thing on the right is called the Compton hump, because it's a broad feature that comes from electron scattering. So photons scatter from electrons in the accretion disk itself. So we fit our models. You see the version called silver is the unblurred reflection. That means no GR. The one called RelSil is a relativistic reflection, meaning you include the GR effect. So in this case, as I showed before, you need both of them, because likely you have reflection from both close and farther away from the black hole. And the panel in the bottom shows the residuals to fit in this model to the data. There is a lot of counts in this data, so it's a highly significant detection, and this is a pretty good fit. The good thing about all these colors that show different spectra is that they're showing a spectra different at different levels of luminosity of the source, and we measure this in terms of the Eddington luminosity. So between 1 and 20%, so you're seeing essentially a change of a factor of 20 in luminosity, but we can fit all this spectrum with the same model. Of course, some parameters will change, and the ones that changes are precisely the location of the inner disk, the edge of the inner disk, and something that is called the high energy cutoff, that is related to the temperature of the corona. So in short, what we're seeing in this system is, as the luminosity increases, you're seeing the disk coming closer and closer towards the black hole. So likely the disk was receded, and that's what the system is not detected in X-rays. And for through some mechanism that is not well understood yet, you'll increase the accretion rate in the system. You start the outburst, start filling in the accretion flow, forms accretion disk, and the disk is just getting closer and closer. It's also increasing the luminosity, likely because accretion rate is increasing. But then you see the temperature of the corona is going down, and this also makes sense, because the more luminosity a plasma will put out, the more it cools down. So this hot gas of electrons will cool down efficiently by just releasing photons. So increasing in luminosity means your corona is getting colder, but we also see this correlated with the disk moving inwards. And just to give you an idea, the changes in the inner edge of the disk that we're detecting with this technique is, if the mass will be 10 solar masses, which is not certain, but let's say that's a typical number for 10 solar masses, we're talking about the order of 45 kilometers for a system that is maybe 8 kiloparsecs away. So that's quite remarkable, in my opinion. This is another example of a very new black hole binary system. Was detected was discovered maybe a year or a year and a half ago. It's called MAXI J1820, and has become one of the brightest, if not the brightest system in X-rays. It has been observed by essentially every detector that I have been able to observe, and this is a very recent paper by Erin Kara that was published in Nature. They were able to not only get a spectrum, but they also got very good timing products. So you can measure time lags between different bands in the spectrum and plot it like here versus frequency. And without boring you with the details, what this means is you're detecting, you're sampling the time scales of the variabilities that you might observe in the spectrum. And the different colors, what they're showing is essentially different time scales for responses between the primary emission and the reflected. So they can, for the first time in this kind of system, they can have an indication that the corona is actually evolving and getting smaller, because what you're seeing is the frequency changes. The changes in frequency, you can connect it to some scale for the meter and for the reflection as well. So this is a pretty exciting new results. We have looked at other systems. We're actually doing a whole bunch of them, and this is another interesting one. It's called XTJ1752. It's very similar to the one I showed before, It has a lot. It got really, really bright in 2011, and then it died, and we haven't been able to detect it anymore. But the data we got was so constraining, was so significant that it pushed the models to the limit. We have to revise all of the models because we realized we needed to do better. Something we learn about this system in particular is that we're able to make differences between models that have different prescriptions for the illumination. So if you, as I mentioned before, if you assume a lamppost geometry in which you put the illumination, the source of photons is just sitting in the axis, it will give you an answer. But if you assume a power law emissivity is something a more extended corona, or the slab corona that I talked before, it will give you a different answer. So the thing that changes here is the inclination. The inclinations between two different geometries are very, very different, or at least a predicted one. So one is 67, the other one is 36. The good thing about this system, we have an independent measurement from a radio jet that says that the inclination should be lower than 49 degrees. So in this case, we can rule out the power law emissivity, and then we see that then in this system, the illumination is likely, or the configuration is likely to be more like a lamppost geometry. So it doesn't have to be necessarily a point source, but it's certainly, the model is calling for a source that is very compact and towards the center. Another system we're working right now is called J1550. It's very similar to GX339. And the good thing about the system, it has very well determined properties. So in this case, we know the inclination of the binary orbit. We know the mass of the black hole. We know many things about it. So we've done archival data analysis with different observatories for the brightest observations we found. And you see this kind of messy plot. It shows all the different spectral components that you need to include to fit this data. So it requires a corona or a non-thermal emission, requires a thermal emission from the accretion disk, relativistic reflection, distant reflection, and also some high energy tail that is possibly linked to emission from a jet. And the difficulty we have here is that with the best fits that we have, after working really hard on it, we always get an inclination that is much, much lower than the binary orbit inclination that, as I said, is very well known. So our inclination is 40 degrees, while the binary is supposed to be about 75 degrees. So this is a very big difference that we don't fully understand. One possibility is that you have a misaligned disk. This is very interesting. You have the possibility for the inner accretion flow to be, or let's say if the spin axis of the black hole is misaligned with the orbital inclination, then you can have an inner accretion disk that is warped with respect to the outer accretion disk. The problem is this wouldn't explain why also the inclination measured from a radio jet that has been observed agrees well with the binary inclination. So another possibility is that you have obscuration of the inner accretion flow. If you think of an accretion disk that you're seeing precisely at a very high angle, like in this case, you can have the disk. This is not infinitesimally small or thing. It might have some vertical structure, and this structure will then block part of the radiation that is coming from the center. And the initial tests that we've done, or the initial simulations, show that what this will do is mostly reduce the amount of radiation that you see on the blue side of the iron K emission. And this is the part that is most sensitive to the inclination. So in other words, you can mimic an iron line or a reflection spectrum that looks like the one for low inclination in a system that is in reality highly inclined. So this is a possibility that would explain what we're seeing in this system. This is really, really important, because then for the first time we're seeing how much information we can get for a single system. We can understand now much more about what is the structure, not only of the whole overall binary, but also the innermost region in terms of inclination and things like that. I think this is maybe I'll skip this one, but just to say that some of these outbursts are also failed. They don't follow the whole transition between hard and soft state. Sometimes they just flare up and they die again. And we get a bunch of this, but when we observe it, we still see signatures of reflection, which means that the inner accretion disk must be getting very close to the black hole, close to the ISCO. So that's interesting. I think I'm gonna go a little bit faster now because I've been talking for a long time, but I just want to mention the newer thing is for the first time we have access to more details of the microphysics of the accretion flow, particularly what happens in the disk. We know that the densities of the disk, accretion disks around black holes can be quite high, according to MHD simulations, like the one shown here, can be as high as 10 to the 23 particles per centimeter cube. And we realized that the reflection models we've been running, they're always assumed some sort of fiducial density of 10 to the 15, which seemed to be okay for AGN, but for stellar mass black holes might not be. And even for AGN themselves, it might be that this is too low. And this affects the shape of the reflection because increasing the density increase a thing called free emission or bremsstrahl emission. So it changes it, as you see in the spectrum on the bottom, it changes the soft energies quite a lot. You have an enhancement of soft X-ray flux. So when we use these models, we tested it on a few AGNs. This is one particular case of an AGN called Markarian 509. These are systems in which we already see some strong soft excess emission that is typically difficult to explain. Some people have argued for a warm corona scenario where you have some other corona, even more mysterious than the first one, trying to come up with an explanation for this soft emission. But what we are able to do now is that with reflection itself, because of the higher density in the disk, as we're assuming now, then it produces more free emission, enhances the soft flux, and therefore we can then now explain this extra soft emission. In the case of black hole binaries, what the high density is doing is helping us with having a more reasonable iron abundance. So it's very typical that when you feed this system, sometimes the iron abundance required becomes completely unphysical. And talking about in terms of the solar value, which is what more or less what you expect, we're talking about factors of a few, maybe even an order of magnitude higher than the solar value. This is very, very difficult to explain because you don't expect such a large enrichment in all the systems consistently. So once again, the enhanced free emission changes the shape of the spectrum, and that seemed to have a positive effect in reducing the iron abundance that you require to feed the same data. We tried that back in GX339, where we were finding something like 5 times solar. Now we got something between 1 and 1.5, which is much more reasonable. So it seems that we're going in the right direction. High density will have effects on the atomic data, which is something we're revising now. You can imagine very, very high densities, the atomic potentials change. There are screening effects and things like that. And that will change different atomic rates. Like, for example, the dielectronic recombination seems to be significantly suppressed. So in short, once again, you don't need to know all the details, but what this will mainly change is the overall ionization of the gas under the same conditions. So if we run something with the standard DR rates, we get a particular solution that says, well, iron 13 in this case is the most dominant iron, but then exactly the same conditions suppressing DR will give you a higher ionization for the same conditions. So clearly, at high densities, we need to worry about these things. And this is what happens to a reflection model, the ones that I showed before. Once you start suppressing DR, it has kind of like a similar effect as the high density by itself. It increases the soft energies flux by quite a bit. but it also seems to have an effect on the iron line, as I'm showing just that panel in the bottom. It produces more iron than the same model with the standard DR. So we're still investigating this. So I'll stop here. I'll say just, X-ray reflection spectroscopy has been great, continues to be a very powerful tool to study the systems. What we can learn, the big things we can learn is evolution of this and corona and systems that change fast, like black hole binaries. We can measure black hole spins for quite a large number of sources. We hope to get better on this. And we are now understanding even more about the microphysics of the accreting flow, and even using this as laboratories to test atomic calculations and properties of the ions on it. So I'll stop here and take any questions. Thank you.
Thank you very much, Javier, for this very nice talk and very complete. I really enjoy all the details. We have a couple of questions from the YouTube channel by Brian Stevens, but I think you answered his first question, which was, does the flux or the density affect the relativistic effect on the ion reflection?
Right. So I'll say just the relativistic. So the relativistic effects are separate from that, but it will affect the shape of the spectrum, and it will therefore affect, it might affect what you get out of, say, what's the spin, what you derive from it. Yeah.
Okay, and then the other question was, low inclination may be due to a magnetic effect. I think he's talking about the degeneracies that might be.
Can you repeat that, please?
Low inclination may be due to a magnetic effect. And it's referring to that degeneracy of that you might be able to measure something with high spin at low inclination, or vice versa.
Well, magnetic fields in black holes are well. I'm not exactly sure what this question refers to. If it is going in the direction of changing the line emission or the way the line looks by something like Zeeman effects, I think the magnetic fields that you expect in black holes are much smaller to do this.
Okay.
I don't think it will work, but maybe the person is thinking something different.
Okay, so Brian, if you're here, please comment on that. Now let's see if our coordinators have questions.
I have a question for Javier.
Yes.
So very nice the talk, Javier, first of all. So I have a doubt. Is it possible with X-rays to try to constrain or to see some deviation, for instance, with GR? Because I don't know if it is in the inner part, or because all the part the corona, it's very interesting, but also
I didn't touch on that, but I actually work in, Alejandro has been involved with this. I work a lot with a group in Fudan in Shanghai that is precisely doing tests of GR with this technique, with X-ray reflection. So the way they're doing it is by everything in our model is obviously built upon the Kerr metric, right? So what they're doing is saying, well, we can change the metric. We can introduce now a metric that is modified. This is a metric in which you have deformation parameters, and if you set them all to 0, obviously you recover the Kerr metric. If they are non-zero, then they just simply introduce different deformations. So the idea is we use this metric, we rebuild the same model using this metric, and then go back and fit and look at the same observations and try to understand, do we always recover all these parameters to be 0, meaning do we always recover Kerr metric, or there might be cases in which not. So I guess locally so far we haven't found any case in which the Kerr metric is being violated. It's a little bit more difficult because this then goes hands to hand with, what is the quality of the data you're looking at. There are many parameters already in the model as it is that they can introduce degeneracies and things like that. So it's not a straightforward way of doing it, but I think it's interesting enough to give it a try.
Okay,
Okay, thank you.
There's another question, and I'm gonna copy it in our chat here, Javier, and it's from Maria Angeles Perez Garcia. She's asking, could we know the origin of some black holes, like for example, a neutron star collapse into a black hole?
I'm not sure how this technique will help you on that. That's an interesting question. No, I don't have a good answer for that. I'll say though that I mentioned briefly in one of the slides, this sort of phenomena are shared by many systems, including neutron stars. So we do see relativistic iron lines in neutron star system with a stellar companion. As far as I know, we haven't seen a neutron star becoming a black hole. Not that I'm aware of. Sorry, I don't have a better answer for that.
Yeah, maybe just by measuring the spin and making population.
Perhaps, yeah.
You might get some information about the origin. Okay, I have a question. So whenever you do those simulations about the spectrum and silver, how does the normalization work? Like whenever you have just different plots. So I was wondering, like whenever you really measure something, how do you compare that normalization?
Well, the normalization will give you information about also the part of the geometry, because whether you have more or less reflection, it might have to do with the way this is illuminated. So this is what we call the reflection fraction. So the amount of reflection to power law that you have.
Okay.
One way to do it, there are different ways. One way to do it is to leave that as a free parameter. So you have that proportionality between the two components to be free. And then it will do what the data wants it to do. But the way to connect it with the geometry is when you prescribe an actual geometry like the lamppost, then the lamppost will tell you what the number is, what that normalization is based on the spin and the coronal height and the inner radius. So those quantities set the normalization. And if you can actually feed the data well with that particular configuration, then that tells you good information about it.
Okay. Thank you. There's another question from Sulov Chalice. Can the inclusion of ionized absorption affect the iron abundance parameter for AGN?
Say the last part. Ionized absorption can affect what, sorry?
Can the inclusion of ionized absorption affect the iron abundance parameter for AGN?
In a way, it might. It's in many AGNs we see what people refer to as a warm absorber, right? So that there is certainly some material absorbing in the line of sight, and that complicates things for several reasons, because you have an extra component to take care of, and if the absorption sort of falls in line with the mission that you're trying to measure, obviously that might complicate things. It used to be a group of people that claimed that through different types of ionized absorption, you could mimic what it looked like a broad iron line. Essentially, they will say, well, it could be that you're not seeing a broad iron line. What could be is that you're seeing a narrow line, but then a continuum that gets distorted by different types of absorption, and you believe and you think that it is a broad iron line. I think that has kind of proven that it's not the case. That doesn't work all the time, first of all, and second, it wouldn't explain the entire reflection spectrum. So to the specific question of whether it affects the iron abundance, I would say no, because the iron abundance is something we measure directly by seeing the emission. It's sensitive to the how strong the emission is, but also how deep the iron KH is. And typically the ionized absorption happens at lower energies. So it is a complication to overall model, and if you don't do it properly, you might end up with spurious results. But I don't think it directly affects the iron abundance.
Thank you. Any other question, guys? Okay, the last one, then I'll do it. So in all those models you presented, like normally what you have is the corona, somehow it has a geometry, then it illuminates the disk, and then we have this reflection spectrum. Do we ever consider the direct component of the corona? And
Yeah, for sure.
Does it have like a huge impact? Does it change?
Yeah. I mean, that is typically the first component you see, the most obvious.
Okay, but that's just going to be, but somehow it's just like featureless, in the sense that it's just okay.
Well, it doesn't have features, but because it's a continuum, it's a non-thermal continuum. But it does have, for example, they have the high energy cutoff, which I went very, very fast over. But you don't see, essentially, you don't always see a power law extending to infinity. At some point, at some energy, it rolls over. And we believe this is because if you are producing this power law by continuously quantizing photons in a hot gas of electrons, photons will gain certain energy. The electrons don't have infinite energy, so they will gain energy up to some point. So that's how we talk about the temperature of the corona. That cutoff actually tell us what the temperature of this corona might be. So it's a very resourceful component.
Okay.
Yeah.
Okay. Thank you, Javier. Thank you, everyone, for your question and attendance. And remember that if you have more questions, you can always email our speakers, and they will be happy to put up the subject, love physics relation. So they will not skip it. Otherwise, just let us know. No, I'm kidding. So thank you very much. Thank you, Javier, and we hope to see you in the next webinar.
Thank you. Thank you so much. Yeah.